Now, so far all the methods we've looked at are non-mutating. In other words, the methods we've run so far don't actually change the list. They just look at everything that's there. So, remember, here is our traversal pattern. Very important to remember. We use these methods at first because they're usually easier. However, there are two very important mutating operations on a linked list. Insert and delete, as we kind of saw from earlier with the Python version of lists. Let's do the simplest version of this, appending a new item to the end of a linked list. Before we do so, let's remember how this works for a built-in list, which is, you set up your list, you do .append 1 or 2 or 3, and it adds to the end of the list. Okay, cool. Linked list append. So we're going to do the same idea. Given any kind of item, append it to the end of the linked list. Now, a linked list only has one attribute, a reference to the first node. This means we have to do a little bit of work before we can append something. Before adding an item, we need to find the currently last node of the linked list and add the item to the end of that. So let's use our template to do so. So traverse to the through the list. Now this is a good start, but here's our thinking. What are we doing with the current item? Well, the answer is nothing. So we actually don't need this. We're just going through to get to the last node. Now, there's a problem with the loop. This loop's designed to keep going until we've processed all the elements of the list, and at that point, current becomes none. But this is actually going too far. We want to stop the loop once we've reached the last node. Now, as a little point here, this is an example of what we call off by one errors in computer science. In other words, our iteration goes through one time too many. Now, to fix this, we're just going to modify our condition. Instead of being while current equals none, we're going to do while current.next is not none, and go through. After the loop, the current is the last node in the linked list, not nothing, which means you might want to have you can have a little check here if you want to make sure that it is a node and the next one doesn't exist. At this point, now, there's no guarantee that current starts off as a node. It could be initially nothing, right? So we don't want to get bogged down with all the handling of this stuff. So we're going to add a comment in here, and it's going to say, what if it starts off as none? We probably should do something. Okay, now, ignoring that, after the loop ends, we know the current refers to the last node in the linked list. So we are in a position to add the given item to the linked list. So we need to create a new node and connect it in. So go through our list to the end. We'll have to do something later about the to-do. Once the list is done, current is the last node, so we can now make a new node using the item we were given. And again, this is where it's important to distinguish between the items and the nodes. The nodes contain the items. And so we need to build a node with the item inside and make the final node of our linked list be that one we just built. Now let's handle that to-do. So we know from our linked list class that the first thing can only be none if it is an empty linked list. So in this case, we just need to make it be the first item in the linked list. In other words, we see what the first node is. If it doesn't exist, then hooray, that's what we're looking at. Otherwise, we have to iterate through and then go through things. So let's actually grab this and try it out, because that's what we're here to do, right? We're here to actually try things. Okay, I'm gonna grab this code. I'm gonna do a little bit of sneaky stuff here. First off, I'm gonna remove the any because my compiler complains when I put any in here. But I think actually the rest of this is fine. And so now what we're gonna do is we're going to append linky.append. It's at a 40, and presumably it should do what we want. My indentation is messed up. That's because this is one space too far over. Let's try it again. Okay. 25. All right, so here's where we were at the last time we ran everything. Let's append a 40. So append, we got a 40. We need to add that to the end of the linked list. First off, is our list empty? It is not, so we can skip this first if statement here. Boop. Okay, so we need to use our current indicator to get us to the end of the list. So let's move along. Not that one, not that one. Okay, here we go. That's the end. So we've looped through. Current is the last node of our list. Now we need to make a new one and put it after. So we're going to build a new node using our initializer for our nodes. Make a node. It's going to have a 40. And next thing is going to be nothing. So here is our new node. And, unsurprisingly, current.next equals new node. So this means current is over here. This next should be here. So you should be able to see which arrow is about to be created. And it is that one, this arrow to go here. And look at that. We got our linked list with the new node added on to the end, exactly as desired. Now, with our append method in place, we can stop creating linked lists by manually fiddling with stuff, because that's messy. And we're going to modify our initializer to take in a list of values, which we then can append one at a time. So instead of just saying first is nothing, we can take a list of items, and for each of them, append that to our linked list. Now, this code is correct, but it is a little messy. And maybe you might be able to figure out a better way to do this without taking so much time. You'll actually see if I try to do this right now, for instance. Let's actually check it in just for fun. So bear in mind right now it takes us like if I scrap this and you look at the execution, it takes about 24 steps for us to set up everything. If I were to do actually, we'll see. Maybe it's actually not too bad. Let's find out. So we're going to append all the items in a list. So items, which is a list. And now instead of doing all this, we're going to do, we'll comment it out. Linky equals link list, and the parameter we're going to give it is 10, 20, 30. I'm actually kind of curious. I mean, maybe it's actually the case this will be faster based on, Python tutor's interpretation of what faster means. Actually, I don't need this last thing down here either. Okay, let's find out. Oop. Ooh, 48 steps to do the same thing. Do we end up with the same thing? Let's go see. So, okay, we got nodes. We got linked lists. Okay, and we're going to build Linky using this. So, okay. We got our list of items. Our items is 10, 20, 30 because those are the things we want to add. Our linked list at the beginning is empty. The first thing is going to be nothing. Now for each item, we're going to do the append operation. So, okay, we got to append the 10 first. All right, we append the 10. So currently we have nothing. Since that's the case, we build a new node, and that is the first thing in our list. So build our new node. It's a 10. This is our new node, and it's going to go right here. Oop, look at that. Sorry about the crossing arrows. It's probably going to get a little messy, but it happens. All right. So we've appended the 10. Now we got to append the 20. It is not an empty list, so we have to get to the end. However, doing that's pretty quick. Current.next is already none, since we only have one element, so we've already reached the end of our list. Now we append our 20 by building a new node. Build a new node. And then stacking that on. Oop. You can kind of see our linked list is starting to get built here. Now we have to add the 30, so same idea. Now we have to traverse through our list to get to our last node. That's the node with the 20 in it. So move along. Here we go. We're in the last spot. And now we build our new node with the 30. It takes a couple steps to do that. Here's our new node. Add that to the end. And 48 steps later, we have built the list that we had before. 48 steps. Last time we did this in 25. Obviously, we were violating some principles there. But you see this took a little bit longer, right? So there is a bit of a trade-off. Now, let's suppose we want a more general form of insertion that allows you to specify the index of the list where you want to insert the new item. In other words, list.insert, but for linked list. So here is the method we're proposing. Insert, given an index and any item. And it's to insert a new node containing the item at the position. Index has to be at least 0. It doesn't really make a lot of sense to be negative. If the index is longer than the length of the list, we have a problem. if the index is the length of the list, then it adds it to the end, just like append. So, example, here is our list. It's got 1, 2, 10, and 200. If we want to insert into the second spot the number 300, then we go 1, 2, then the 300. So bear in mind, remember, when I say second spot, I actually mean at index 2, remembering that we have index 0, then index 1, then index 2. And if I want to insert into the fifth position minus 5, well, right here, or not fifth position, but into index 5, this doesn't have an index 5, it is length 5, so it just appends it to the end. So, just like append, our first step is to traverse the list till we find the right spot. And if we want the node to be positioned there, we need to access the node right before it. So we're going to need to modify our template a little bit, not just to store the current node, but also the index of that node. So here's our insert. We start off at the beginning. The index of that is 0. While we haven't reached the end of the list and we haven't reached the right index spot, we move to the next one and increment our index. This loop condition is a little more complicated, so let's break it down. We're saying that the loop should keep going whenever we've not reached the end of the list, meaning the current node is not none, and the index is less than the target we're going for. So this means when the loop is over, we have two possibilities. Either we've reached the end of the list, which is where we need to append stuff to, or we've found the spot that we need to insert into. One or the other. It could be both, potentially. But one of those two things has happened. So we need to break our code into two possibilities, because it could be either one. So first possibility, current might be none. If it is, we need to do one thing. If current isn't none, then we've hit the other possibility, which we need to consider. So if current is none, this means this doesn't have a node there. In other words, it's out of bounds. So we should raise an index error. On the other hand, if current is not none, we've reached the desired index and can insert the new node using the strategy as append. So let's, well, this is almost it. So what do we have so far? We traverse through counting by the index and looking at each of the nodes. If the node is done, that means that index -1 is too far. We can't insert the item, so an error has happened. Otherwise, we have reached the target index. It's within the bounds. We insert the item, and the way we do so is we build a new node and put it there. Almost. Unlike append, the current node may have other nodes after it. You need to make sure you don't break the chain. Simply setting the current node .next to be the new node means we've lost the one that comes after that, and subsequent nodes after that one as well. So before we overwrite current.next, we need to update the new node so it refers to the old position. And this is basically what I mean. We make a new node. Its next is going to be the one after it that originally had an arrow going to it, and now we can put this one here. So this is kind of, I think it's actually like really hard to explain without seeing it. So let's see it, right? Okay, grab, go over here. I'm going to insert. This should be okay, I think. I don't expect there should be any errors here. We're going to do linky.insert, and let's insert a 25 into position 2. So 225. Actually, you know what? Let's insert it a little higher just so you can kind of see the redoing of the arrows, and we'll build this linked list up a little bit. 40, 50, yeah, sure. And we'll put a 25 into index 3, so that should be 0, 1, 2, and so the 25 should go between the 30 and the 40. So I'll skip through a bit of this because a lot of this is just building the linked list, which we know how to do here, so this shouldn't really be a surprise to you. 10, 20, 30, 40, 50. Part I want to get to is the actual insert. So okay, here's our linked list. At the beginning, we got 10, the next one is 20, then 30, then 40, then 50. Okay, and they all got little arrows that say the next one is this one, which next one is this one, next one is this one, and so on. Okay, now, we want to put in 25 into position 3. We start here. Here's our current node. And we need to traverse through to figure out, are we at position 3 or have we reached the end of the list? Either one means we need to do something. So far, everything is cool. Our current index is 0, so we need to move through. Okay, move to the next one. Our index is now 1. So this red arrow is where we are currently at. And our index is 1, as you can see here. Next, move over to here. Red arrow. Our index is now 2. Keep going. And now, okay, now we stop because our target index is 3 and index minus 1 is 2. So we've reached the spot where we need to start doing stuff, right? Our current node, 30, is right before where we want that 25 to be. So, okay, let's pause a moment here. Current is not none. We obviously have a big old red arrow here. So that's cool. We can skip that in our code. We need to build a new node with our 25. So down here, we're going to make our 25. Okay. Now, we want the 25 to be in the middle here, which means we need this arrow to point to 25, and we need 25's arrow to point to 40. So that's the 2 lines. It's only 2 lines of code, but that's what we need to do. So new node.next is current.next. What does this mean? Well, our current node is the 30. The 40 is what we want to get a reference to. So our new node.next down here should be set to wherever this is pointing over here. And so let's have that happen. Bloop. Just like that. This means now we can take this red arrow and point at the 25, and our linked list is again a linked list where we can go here, 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 and follow the arrows basically. So, yep. It's obviously looks like a little, not a straight linked list, but a linked list nonetheless, where we got 10, then we got 20, then we got 30. If we follow the arrow, we then get to the 25 down here, which then points to the 40 and then the 50. So we have our continuous linked list. It doesn't have any breaks in here. We can still get to all the elements that are in our linked list, and we've inserted in a new element. I really recommend giving this a shot, like trying it out with some values, testing some different examples of linked lists, different nodes into different positions and so on. It really gives you like kind of an uncomparable way to understand how this whole process works, aside from just the example that I've shown you. So, okay, common mistakes. When writing mutating methods, we very often update the links of individual nodes to add or remove nodes from a list. But you have to be very careful because the order in which you do things makes a big difference. For example, if we went back here and looked at these 2 lines of code and changed the order, it would shatter. And I'll actually show you why. Okay, so I believe it was step 101 where we start doing the so here's our new node, we need to put it in the right spot. So, 102, 103. Okay. Let's just switch the order in which we change those arrows and see what happens. So the way that we should do it is we figure out where the 40 is, and we make the new node point there. Then we make our current node point to the 25. Let's try the other order and see what happens. Literally just going to flip them. Where is it? Insert. We're just going to put this line of code before the other one. And observe. Again, if you don't know what's going to happen with code, let's just try it out. Okay, 101. Okay, up to this point, everything is still the same. But this time, instead of making this point here first, we're going to make this point here first. So current.next is the new node. So this is going to point here. Wait, what happened? I'm being kind of facetious. You notice the 40 and the 50 are gone, right? Well, that's because we have no way to get them anymore. Since 30 is no longer pointing to 40, we don't actually have any way to get to the 40. When we do the next line of code, new node.next is current.next, where do you think the arrow is going to go? It's just going to point to itself, because that's what the next thing is. So this order is really critical. If you mix up the order, it straight up doesn't work, and you actually lose data. It just gets deleted. This 40 and 50 here, bloop, gone. let's fix that, because that's obviously a big error. Where are we? Down here. But that's basically what this is about to explain, which I'll reiterate just for fun. The order of link updates in the final else branch doesn't work if you flip them. On the second line, current.next has been updated, so its old value is lost. That 40 and 50, out of here. The second line is now equivalent to writing new node.next is new node, which points to itself, not what you want. The reason this is so insidious is because it's literally one small difference from the other code. Character for character, all the same letters are there, just the order of two statements is flipped, which shatters the whole thing. The only way you would probably notice this is by literally looking through and going step by step and seeing what happens. Now, to mitigate this problem, we can take advantage of a pretty nice Python feature called multiple/simultaneous assignment, which looks something like this: a comma b equals 1 comma 2. The beauty of this approach is that all the expressions on the right are evaluated first before being assigned to things on the left, which means that the order doesn't really matter too much. So these two are equivalent. Current.next, new node.next equals new node current.next is the same thing as if you just flip the order of them. This is a good trend to get into doing, because it prevents you from potentially making the mistake up here of having the two assignments in the wrong order. Strongly recommend using multiple assignment in your code when working with complex state updating. Now, our insert implementation has a problem. What if index is 0? In this case, it doesn't make sense to iterate to the index minus 1th node, because that would be -1, which means you could actually kind of do that, right? That means go to the end. Now, this is a special case which we need to handle separately by modifying self.first, because we're inserting to the front. So if the index is 0, we should specifically be making a new node and making it be the new node, and making new node.next be what was self.first. And notably, self.first could have been a node, but it also could have been none, which means you probably want to be able to assess which one of those it is and set it to be that. And so here is our updated and improved version of insert, which I recommend you try for yourself. Now, the analog of list.append is list.pop, which lets you remove an item from a specified index. Because this is like an insertion, I don't think we'll do the whole code here, but here are some steps basically. And recommendation, try this out. You really should. Give yourself some practice on actually coding this. So pop removes and returns a node at an index. Index being something greater or equal to 0. There will be an error if the index is bigger than the length of the list. So if you have this list and we want to pop what's at 2, it should return to us 0, 1, 2, so the 10. If we want to pop the first element, so at index 0, should give us the 1. Now, here is some pseudo code, not actually Python code, but an instruction as to how you should do it. If the list is empty, the index is at bounds. Otherwise, if the index is 0, you remove the first node and return its item. Otherwise, iterate, traverse through to the index minus 1th node and update all the links to remove the node at the index and return the item from that node. Doing this exercise, I think, is a very good confirmation that you understand how to work with linked lists, and should give you some confidence that you kind of know what you're doing when it comes to the topic.